So today's lecture is on the 2 degree of freedom systems. So we are going to take a look at the equations of motion and free vibration response. So basically in this system, we're going to take a look at a system where you have two masses as such, and you're going to see that you do have two displacements. Maybe you will also have slightly different figure as what we're going to see in these notes, but however you are going to deal with a system that is what we call 2 degree of freedom system. So let us take a look at in this lecture. The learning objectives are as follow, where you're going to take a look at the difference between the generalized and principal coordinates, and also look at the EOM, equation of motion, for the 2 degree of freedom system. You need to be able to derive this and express the expression. Since it's 2 degree of freedom, you're going to need to write it in matrix form, and some of the characteristics, you need to determine the characteristics equation, because from matrix form you're going to see that you're going to have a quadratic equation, and you need to find the undamped natural frequencies and associated mode shapes. Alright, so most engineering systems are continuous and have infinite number degrees of freedom, but for simplicity of analysis, continuous systems are often approximated as multi-degree of freedom systems. So if it's a multi-degree of freedom systems, you can actually solve it using set of ODE, or ordinary differential equations. If continuous system, you're going to take a look at that in future, in the towards the end of this course. That one you're going to use the PDE, or partial differential equation. So there is one equation of motion, for each degree of freedom. So in other words, if you have n if you have n natural frequencies, each associated with its own mode shape for a system, then you would have n degrees of freedom. In other words, if you have 2 degrees of freedom, that means you're going to see that you're going to have 2 natural frequencies. So that's what it means. So a continuous system can be approximated as a multi-degree of freedom system by substituting the distributed masses or inertia with a finite number of lump mass rigid bodies. So this should be the assumptions. You have a finite number of lump masses or rigid bodies. It's assumed to be connected by massless elastic. So these are also assumptions. Your elastic or your spring and damping are massless. Linear or angular coordinates are used to describe the motion of the lump masses or rigid bodies, and number of coordinates necessary to describe of the motion of lump masses or rigid bodies defines the number degrees of freedom of the system. I think this one we have mentioned the definition of degrees of freedom in our earlier notes. This is one of the examples. Number of degrees of freedom equals to the number of masses in the system times the number of possible types of motion of each mass. So as I mentioned just now, basically you're going to have n equations of motion when you have n degree of freedom. So as I said, if you have 2 degrees of freedom, that means you're going to have 2 EOMs. When you have 2 EOMs, you cannot, when you want to solve it, you have to write it in the form of matrix. So these equations are generally in the form of coupled differential equations. And each equation involves all the coordinates. If a harmonic solution is assumed for each coordinate, the equation of motion lead to a frequency equation that gives n natural frequency. So as I said, for 2 degrees of freedom, you're going to have 2 omega n. So sometimes we call it omega 1 and omega 2. So during free variation at one of the natural frequencies, the amplitudes of n degrees of freedom are related in a specific manner. So this is what we call the normal mode. Okay, so take note, we're going to use this concept in the next lecture. Okay, what it means by this. So it's basically what we call normal mode, principal mode, or natural mode of vibration. So it's all related for each natural frequency. Under each natural frequency, it has its own mode. In other words, if you have 2 degrees of freedom, you have 2 natural frequencies, so you do have 2 modes. If an arbitrary initial condition is given to a system, the resulting free variation will be a superposition of the normal modes of vibration. If the system vibrates under the action of an external harmonic force, the resulting forced harmonic vibration takes place at the frequency of the applied force. So, the condition of resonance is still the same. Under harmonic excitation, resonance occurs when the forcing frequency is equal to the natural frequency of the system. So in other words, if you have 2 degrees of freedom, then you would have 2 conditions. Yeah, you have the first frequency and the second natural frequency, so it will occur twice. Yeah, the resonance will occur twice. The configuration of a system can be specified by a set of independent coordinates. Okay, so the independent coordinates can be physical parameters such as length, angle. Okay, it can be other things, for example, temperature, pressure, and so on. Yeah, any such set coordinates is what we call generalized coordinates. Okay, there exists a particular set of coordinates which uncouple. So you're gonna see as well that there is another set of uncoupled equation of motions. So where each equation of motion contains only one coordinate. Okay, such set of coordinates is called principal coordinates. So the one that we're going to deal in this lecture is the generalized coordinates. Okay, we're going to take a look at the principal coordinates later on when you actually have the you can actually try to make the set of coordinates uncoupled. Okay, we're going to see that later. Yeah. So the normal one that we use may be displacement or angle. That one is what we call generalized coordinates. Alright, so let's say we have this type of system. So I guess this is actually from the textbook. So there is something wrong with this arrow. Okay, I'm going to show this derivation in another video. Okay, why is it wrong and how do you do it if it's because this figure is when you assume tension. So I'll do a separate video on the derivation. So let us take a look at go ahead. So from this, if you draw the free body diagram, so as usual, you need to draw the free body diagram, and then after that get the equation of motion. So you have to write for each mass, yeah, M1 and M2. So you get this equation. So you can see that in this case, okay, when C2 and K2 equals to 0, okay, that means this is 0. Alright, okay, then the equations become uncoupled. Okay, what it means by that, if that is 0, so this expression, the whole thing, okay, because you times 0, then sorry, so K2x1, yeah, it will become 0. Okay, you don't have that K2x1. then you still have that okay, this one is 0 then. Okay, you still have the c1 x dot 1 and k1 x1 and so on. Yeah, so the equations become uncoupled, which implies that the two masses are not physically connected. All right, so from there, okay, from this you can write it based on these two equations. You can actually write it in terms of matrix form, where you can rearrange in terms of x1, and also you have your x2, isn't it? So you rearrange, if you rearrange, so this is actually a vector of x1 and x double dot 1 and x double dot 2, okay, and same as this okay, so this x double dot vector, okay, is represented by x double dot 1 and x double dot 2 as same as the x dot and also the x. Okay, so if you remember, matrix is basically a row, for example this one, matrix M, if you times with this vector, okay, you will get M1 row times column. So each of these element you need to times the x double dot 1. So you have M1 x double dot 1 plus 0. Okay, so then the first expression you will get mx double dot 1 plus 0, and then another equation, another line. Okay, you're going to have two equation of motion. Basically the next line will be 0 plus m1, yeah, m1. So you have to times a row times this column. Yeah, so you get 0 plus m2 x double dot 2 and so on. Okay, I'm just doing for this one, what is it for m x double dot? What does it mean by that? Yeah, so basically how do we get that? Basically it's from this equation 1 and 2. You rearrange the terms in terms of x1 and x2, x dot 1 and x dot 2, and x double dot 1 and x double dot 2, and you rearrange it in this matrix form. So I really hope you can remember your linear algebra perhaps, which has the basics of how you write it in terms of matrix form. Alright, so don't forget, if you have input to the system, then of course you would have the force vector there. If not, in this case we want to find the natural frequency, so the F will be 0. Okay, so this is free vibration, so it's 0. So now your solution will be 2, x1 and x2. Remember, you have two masses, so you have two displacement. If you actually substitute from here, okay, you take x dot 1, okay, what is it, and also x double dot 1, what is it? Okay, so you just substitute into this equation. Okay, so do the same thing here. You have to take x dot 2 and x double dot 2. Okay, basically if you look at this equation, you only have x double dot and just x, isn't it? Okay, so you just substitute all this x double dot and x into this equation. So if you do that, so you have this basically. So you still have these two equations. If you can actually rearrange everything. So if you put 0, you bring this whole thing to the other side of the equation, so that term will become 0 as well, same as this one. Yeah, you bring it to the other side, so at the end it will become 0. So you will left with this term on the left hand side of the equation. So rearrange, so you can see that everything is in terms of capital X1 and capital X2. 2. So from there, you can get it in terms of this. Okay. So from here, you make it, rearrange the terms in terms of x1 and x2. So make it in a matrix form. So how do you do that? You take the determinant. Basically, you take the determinant, okay, to solve for your omega. Basically, what you want to solve here is you solve for your omega, because after you take your determinant, you will get in this form. Yeah, this is after you put it in terms of determinant. So you collapse it into one equation. So you can see that you have what we call the characteristic equation. Okay, based on this characteristic equation, notice that the power is 4, 2, and there's no power here, right? So that means if you use characteristic equation, if you use your calculator, for example, basically what you key in your calculator is basically this will become your A, this will become your B. Remember, your calculator can solve the characteristic equation. This will become your C. So input in your calculator and your answer is actually omega square. Okay, you're going to get two answers. The first answer is omega square 1 or omega 1 square, and the second answer is omega 2 square. Why square? Because your power here is 4. Okay, your power here is 2. So as if your x in your calculator is actually, in calculator, x is equals to omega square. Okay, so then this is very important. Whatever your answer in your calculator is actually in terms of square. Then if you actually want to solve for your omega, you have to take the square root. Okay, so your final omega 1, it should be square root of the answer number 1, and your omega 2, it should be the square root of your answer number 2. So after that, so this is the long way. This is using the quadratic equation to solve the characteristic equation. As I said, normally for calculations, you just use your calculator to get the value. Once you get that, then you can actually substitute into the equation. Okay. You already have the frequencies. Yeah. Alright. So then you can also take a look at how you determine the mode shape. Alright. So after we've got the omega 1 and omega 2, you can see here we have the solutions for x1 and x2, and you also have the amplitude, capital X1 and capital X2. So normally we want to use capital X1 and capital X2 is actually depending on the natural frequency. Previously we just have one natural frequency, but now we have two. So there is a way of finding the mode shapes. So this is how you can find the mode shapes. One of it is by having to write it in terms of this ratio. So R1 is actually ratio of capital X2 and capital X1. Okay. This one denotes that it is corresponding to the first natural frequency. Okay. The superscript denotes that it is at which natural frequency. So now you do have two amplitudes. One is at natural frequency 1 and another one is at natural frequency 2. So basically you have four amplitudes here. X2 1, X1 1, X2 2, X1 2. So you have 4. So how do we get this equation? So please refer to slide 15. Okay, I'm going to show how we get this equation. Basically, if you refer to this slide 15, if you remember, after we rearrange this, you can see that you can write this in terms of an equation like this. Okay, so I'm basically you just times x1 and this one times x2. So rearrange the terms in terms of x2 divided by x1. So you have this equation. So you can see back slide 18 just now. Sorry, slide 20, yeah? Slide 20. So if you go slide 20, so you can see that this equation is the same equation that I've shown here. Alright, so you can go back to slide 20. So from there, okay, actually it's the same. Either you do this way, R1 or R2, okay, you're going to take a look at the actual mode shapes that you're going to calculate. Is basically we can say it depends on the question. Some questions they want you to express the mode shapes in terms of ratio. Okay. Sometimes the question wants you to express it in terms of a vector like this. So you have to look at the question. So but basically you need to get the value, the relative value of these 4 parameters, yeah? These 4 parameters, basically. So then you can rearrange in terms of ratio or in this form. So basically you want to get those parameters evaluated at a respective omega. Okay, maybe after an example it will be more clearer. So you can also express the expression as such. And this is an example of force vibration of a 2 degree of freedom system. Alright. So it's a torsional system with 2 disks. So either you have it in a linear system or a translational or torsional system. The derivation are quite similar, but now you have, instead of linear form, you have torsional stiffness, you have J instead of M, and you have torque. And your displacement is are called as thetas, okay, not X anymore. So if you rewrite the equations, you can actually see that the free vibration analysis of the system is as such. Okay, this is the EOM basically. Alright, so I guess that's all for this video. We'll take a look at how we derive the equation. Maybe with an example, it'll be more clear. Okay, thank you.